All right, so next up we have our third unit, and different physics teachers and different physics textbooks do this in a little bit different of an order than I do. I like doing energy next because I think it's a good, easy way to follow up some of our motion stuff. We've been spending, so much time talking about quantifying motion, and I think that energy is quite an often overlooked but easier way to quantify certain things. So really, there's two main chunks to this, and that is the concept of energy and the concept of work. And we're going to break that down in this section. So similarly to the last unit, we're going to start by creating a catalog of energy. Now, your sixth grade definition of energy, you said was the ability to do work. And we are absolutely going to talk about work and how it relates to energy. But energy is like, it's describing what something has in a, and it's kind of weird. It's like a quantifiable amount of what something has. But really it's kind of like a physical characteristic, like it has this type of energy. So let's start with that. We're building a catalog of energy, and let's get right into that. So we have to start. Let's talk about kinetic energy. And kinetic energy is the energy of motion. So any object that is moving has kinetic energy, and the magnitude of that is 1/2 mv squared, and we use the symbol K for that. Now, one thing I want to draw your attention to is the fact that this velocity is squared. So everything that we've been doing up to this point, Unit 1 and Unit 2, we've been primarily using vector quantities. Vectors, of course, have both magnitude and direction. So if I accelerate, I'm accelerating at 5 meters per second squared in the positive direction, whatever. Everything with energy, on the other hand, though, so energy, again, it's like a physical trait. These are all going to be scalar quantities, meaning that they don't actually have a direction. Now, that's kind of weird because some of the stuff I'll talk about kind of does, but really it doesn't. Energy is all scalar, and which means that I always have positive amounts of energy as well. So next up, so that's kinetic energy. We also have gravitational potential. So any object, any object that is stored some height above the ground, mgh, and that has gravitational potential energy. Another type of potential energy is elastic potential. An elastic potential is energy stored with the stretching or compressing of molecules. So that's 1/2 k delta x squared, where k is, of course, the spring constant and delta x is the displacement from equilibrium. And again, before we had the spring force was k negative kx, and that signified that it's always opposite the direction of compression. But we should always get positive numbers when we're quantifying something's energy. So these are all scalar quantities. And these are really, honestly, these three are the main ones that we talk about. But we do get into this concept of thermal energy. And thermal energy means that it's energy that's essentially lost due to friction. Now, we do have a formula for it. And that is, it's the force, whatever your force of friction is, times the displacement that it's gone through. And we're going to talk about that a little bit because that's actually a great segue into work. But thermal energy, is, quite often, instead, we just say it's whatever energy we no longer have. It's energy that's lost due to friction. If you take physics 2, we get into the concept of chemical energy and nuclear energy, but we're not going to worry about those. Those I'll also get into in chemistry, but we're not going to worry about that right now. So that's our quick, really easy, much less than forces. That is our catalog of energy. And of course, what are we going to do with this? Well, let's start with the concept of work. Um, and work is where energy comes from. So if I'm doing positive work, that means that the change in energy is increasing or energy is entering the system. Negative work, change in energy is decreasing, energy is leaving the system. And so, what is work then? Work is the adding or subtracting of energy. So our formula for work is force times displacement, and that's why our our thermal energy equation is so nice, because it's force of friction times displacement, and this is work in general is just force times displacement. So before a lot of times we talk about the perpendicular component of the force. Now we're actually talking about, though, the parallel component of the force times the displacement. So I'll give you an example. Going back to our free body diagrams, if I am pulling a box, I am exerting a force on that box. Now only the x component of that force is gaining energy. What kind of energy is it gaining? It could be gaining some kinetic energy. It could be gaining some, if it has friction, it could be gaining some thermal energy, right? So it's the perpendicular component, the parallel component, otherwise known as the component that's in the direction of travel, that is actually gaining energy. Okay, so our formula for work is actually really simple then as well. And what do we do with this? So there are two main concepts that come up. First is the work energy theorem. And that's really simple. The work that we do on a system equals the change in energy of the system. So if I'm doing work, I'm adding energy into the system. Or I could be doing negative work and I could be taking energy out of the system. So if I have 1,000 joules of energy, I can do positive work and give it 2,000, or I can do negative work and give it 0. And that seems quite simple, but really it is. Until we get into the second main concept, which will be the conservation of energy theorem. So the conservation of energy means that if there's no work being done, then my initial energy, whatever energy I start with, the amount of it, my initial energy has to equal my final energy. So there's no change in the total amount of energy in the system. So let me go ahead and get into my analogy with this. You work a job, right? Your working gives us the work energy theorem. So work we know is force times displacement. Well, instead, let's say it's the number of hours times your hourly wage. That gives you how much money you get. So the amount of work you do, the number of hours you put in, gives you your money. That gives you your money that you're starting with. In our case, it gives us our energy. Now, once you have that money, then we get into the concept of the conservation of energy. So the conservation of energy says whatever money we start with, we have to end with. So you get your paycheck, right? And the government it takes out a whole bunch of money from you. So you lost that money. Let's say you had to pay your car insurance, you had to pay your cell phone bill, right? There's money leaving. You got to take your girlfriend out on a date. You got to pay for gas to fill up your car, right? You got to buy lunch. You got to buy whatever. You buy some clothes. You buy some Grand Theft Auto, shark cards, whatever. And now all of a sudden you're out of money. Well, did you lose that money? No. That money is now represented in different ways. And that is the conservation of energy. Energy can be transformed from one type to another type, but it cannot be created or destroyed. So the big thing with energy is never created or destroyed, only transformed or transferred. Work would be the concept of transfer. The conservation of energy is a concept of transform. So energy is only transferred or transformed, and that's how we can use it to solve some problems. So let's take a look at one quick example. So I'm going to draw like a big grassy hill. Okay, there's a ball at the top of that hill. Now, in previous units, we could only have a hill. Well, we couldn't have a hill. We could only have a ramp. And then we said that as it goes down, A equals G sine theta. That's really all we've done so far. Now, with this hill's a little bit more complicated, right? It's got all these little points of inflection. So here it's kind of like in free fall. Here it's kind of like slowing down, again, speeding up, slowing down, right? So there's so many different accelerations because the angles are changing. And we can't use forces either because the normal force is changing, so the acceleration is changing. So I can't use our kinematics or dynamics to solve this. So conservation of energy is great when all I care about are 2 points. I care about an initial point and a final point. Whatever happens in between doesn't matter. That's why this is so simple and so elegant. And all I'm saying is that whatever energy I start with, I have to end with. And that is the conservation of energy. Now, maybe I did work to get the ball up to the hill, or to get the ball up the hill, I had to lift it up, whatever. But whatever energy I start with, I have to end with. And that is the law of conservation of energy. So really easily, I say what energy or energies do I start with? Well, I start with gravitational potential energy. What do I end with? Well, I end with some kinetic, and let's, for good measure, say thermal as well. So I can use our formulas, right? mghi equals 1/2 mvf squared plus the force of kinetic friction times. Oh, this is why this gets a little confusing, and often I don't break this down. My force of kinetic friction, that's the coefficient of kinetic friction times the normal force, and my normal force is always changing. That's a little complex. So instead, we typically just leave this in terms of thermal energy unless I'm sliding across a flat surface. So I can use the conservation of energy to solve for an unknown. And a lot of times with these problems, I say, oh, this hill is 4 meters tall. The ball weighs 3 kilograms. It ends with a speed of 8 meters per second. How much energy did I lose due to friction? So I have all these variables, and that's what people get overwhelmed with, is that there's so many variables. But a lot of times you have all of the information, or a lot of times things cancel, like the mass can cancel too, right? So there's all these different problems that we looked at that can use the law of conservation of energy to solve, and it's really, really simple. Now, there's one other concept that we got into, and that was the concept of power. Now, power is really simple. It's how much work we're doing in a given amount of time. So it's our change in energy over time. It's not just how much energy you add or subtract, it's how rapidly you're doing it. This is measured, of course, in watts. And the way that I always remember this, if Arnold Schwarzenegger was in my class and we were learning about the conservation of energy, and he was confused on something, he would raise his hand, and I'd say, yes, Mr. Schwarzenegger, and he would say, what is the unit for power? And of course, he would be correct in that, because the watt is the unit for power. So power is really simple. It's how much or how rapidly you translate energy. Now, we do take a look at this again later in terms of electrical energy, and power then is the current times the voltage, which is how rapidly we burn off electrons, essentially, or how rapidly electrons are moving. So there's more things that it applies to later on in the year. And that's it for power. One last thing that we kind of looked at, and this is where our textbook differs from what I like to do, and that's taking a look at energy in collisions. Now, anytime something collides with something else, conservation of energy is not what you should jump to. You shouldn't be like, yeah, I'm going to use conservation of energy to solve that. You should always go for conservation of momentum, which is our next unit. But we can break collisions down into three types of collision, or two types of collisions, and I'll talk about a third concept. So we have elastic collisions. Elastic collisions are bounce collisions. This means something hits something else, okay? And if it's perfectly elastic, that means that it's perfectly bounced. No energy is lost due to friction. We can also have inelastic collisions. Inelastic collisions are a hit and stick. So hit and stick collisions. So hit and stick means they collide and they stick together. So like two cars hitting each other and one comes like kind of impaled in the other one. Now, when I think about energy, no matter what, in an inelastic collision, there is an inert loss of energy due to thermal energy. No matter what, it has to be. Due to the rearrangement of molecules, there is a loss of energy to thermal energy. So anytime I have an elastic collision, I can't use conservation of energy because I don't have a way to quantify this. It's impossible for me to predict exactly how much thermal energy will be lost. So anytime I have an inelastic collision, I have to go conservation of momentum. Now, with elastic collisions, there's another concept, and that is this concept known as mechanical energy. Mechanical energy is just the sum of all the usable energy. So it's the potential plus the kinetic. And if I have it, I could have like elastic potential as well. So it's mechanical energy is a sum of potential and kinetic. So with elastic, if it is what is known as a perfectly elastic collision, then mechanical energy is conserved. So I could use the conservation of energy. Specifically, if something hits something else, it can transfer its kinetic energy if it is perfectly elastic. And then I can use the conservation of energy to make predictions on that. Here's the problem with that. Let's say I have a cart here, and it's got a plunger on it, and that plunger is perfectly elastic, and it hits the wall, and it bounces back. And if it bounces back with 100% of its initial energy, then I can say that kinetic energy is conserved. However, before it was going this direction, now it's going this direction. So it's switched directions, which is a little confusing because I don't actually see that. I don't have negative energy because energy isn't negative. Kinetic energy is always, always positive. So that's why quite often we don't use energy to evaluate collisions. Now, energy is conserved always. Energy is always, always, always conserved. Even if it hits the wall and collides and sticks and stops moving, does that violate conservation of energy? No, that energy became thermal energy. All right, and it's just lost to the environment. Energy is always conserved. Mechanical energy is not always conserved. Mechanical energy is conserved in an elastic collision. Mechanical energy is not conserved in an inelastic collision. So again, therefore, anytime I look at collisions, momentum is always where I want to start. And we'll take a look at that in the next segment. So that was quite possibly the quickest video we could have had with this, and that makes sense because this was one of our quickest units. We started by building a catalog of energy, and we talked about the different types of energy that we were going to use. Work, that's where energy comes from. We do work to get energy. Power, that's how fast we do work. And then you can use the conservation of energy to look at a before case and an after case, drawing your attention back to the work thing over here. Your work is your change in energy. That's the work energy theorem. So if I do work, I increase energy. But if it's a closed system, I use the conservation of energy. And then we did briefly look at energy and collisions, but we're going to look at collisions way more with momentum in the next segment.